Good morning. In the previous class, we discussing about module 2. In that, we already discussed introduction. Okay. Here, what are the basic architectural features are required? Okay. We already discussed this one, and also we are discussing about DSP computational building blocks. In this, we already discussed multiplier. Okay. Next one is shifter. Okay. The shifters are used to scale down or scale up operands or the results. Okay. These avoid the errors resulting from overflows and underflows during computation. Here, the registers which have some particular size. If it is, for example, you can consider any accumulator. If it is 16-bit means, okay, if it exceeds 16-bit, then what will happen? Overflows. Okay, to avoid that one, we can use the shifters. Okay, what is the use of shifters? The shifters which can do the scale down or scale up. Okay, scale down means we can divide the particular value by some value. Scale up means increase the size of the value. It means scale up multiply by some scaling factor. Okay, next one is the following scenarios give the necessity of a shifter. While performing the addition of n numbers, each of n bits long, the sum can grow up to n plus log of n with base 2. Yeah, actual size is this much. How much? N. Okay. There is excess of this one when we do the addition. If the accumulator is of n bit long, then an overflow error will occur. This can be overcome by using a shifter to scale down the operand by an amount of log of n with base 2. Here, the size of the sum is grows up to log of n with base 2, but accumulator which can hold only the n bits. That's why to avoid the overflow, what we can do? We can scale down the input operands by log of n with base 2. Okay. Similarly, while calculating the product of while calculating the product of two n-bit numbers, the product can grow up to 2n bits long. Generally, the lower n bits gets neglected and resulting in loss of accuracy. Okay. Next one. Finally, in case of addition of two floating point numbers, one of the operands has to be shifted approximately to make the exponents of two numbers equal. When you are doing the addition of floating point numbers, okay, their exponent size we can make it same. To make the exponents equal. Okay. Next here, barrel shifter. In a conventional microprocessor, shifting is normally implemented by an operation similar to the one performed in a shift register. The operation takes one clock cycle for every single bit shift. To shift a single bit, which requires a one clock cycle. Okay, what will happen? The performance is decreases. I mean, which can take to shift all the values, which can take more number of the cycles. Okay, see here, it is not desirable for DSP applications, which generally involves more shifts. In other words, for DSP applications, as speed is the crucial issue. Several shifts are to be accomplished in a single execution cycle. This can be accomplished using a combinational circuit known as barrel shifter. Okay, in a conventional shifter, okay, each single bit shift requires a one clock cycle. Okay, what will happen? The performance is decreases in terms of speed. Speed is decreases. To do the all the shift bit shifts at the same time in a single execution cycle. This can be accomplished by a, just remember here we call it a barrel shifter. Okay, barrel shifter which connects the input lines representing a word to a group of output lines with the required shift determined by its control inputs. Later we'll discuss the block diagram of this structure of the barrel shifter. Okay, the input lines representing a word to a group of output lines. Okay, here the shifts are determined by some control inputs. Later we'll discuss what are those control inputs. Okay, for an input of length n and shifts from 0 to n minus 1 bit position to the right or left are to be implemented. The control input requires log of n with base 2 lines to determine the number of bits to be shifted. Okay, here the control inputs which had to be log of n with base 2 bits, log of n with base 2 lines to determine number of bits to be shifted. Okay, further an additional line is also required for the control input to indicate the direction of the shift. Okay, addition of this one, okay, how many number of the bits to be shifted. Okay, some the control input which also indicate which direction to be shifted, either it's the right shift, either it's left shift. Okay, bits shifted out of the input word are discarded and the new bit positions are filled with zeros in the case of left shift. Okay, when we shifting the values left side in this direction, okay, for example 1 1 0 1, okay, consider when you are shifting left side means it becomes 1 0 1. Okay, here this empty place, this value will be shifted out of the box. Okay, then what will happen? This bit is bit position is empty. This is filled by zeros. Okay, in the case of right shift, the new bit positions are replicated with the most significant bit to maintain the sign of the shifted result. For example, here you can consider same 1 1 0 1. One one zero one, right side. Okay, see here. This one will come here, this one will come here, and this 0 will come here. That means 0 here, here 1, here 1. Then what about this position? Okay, this value, what is the most significant value here? It's 1, right? This is filled by 1. This is right shift. Okay, here input and output. Yeah, the control input, control lines or control inputs which indicate the number of bit, how many number of the bit positions to be shifted. That one, and also which indicate whether it's left shift or right shift. This is the block diagram of structure of the barrel shifter. Okay, and this is the example for 4-bit shift right barrel shifter. I already asked this question for second IA. Sorry, first IA. Okay, please go through this. Here, above figure shows an implementation of barrel shifter with 4 input bits A3, A2, A1, A0 and 4 output bits B3, B2, B1, B0. Using this shifter, it is possible to realize right shift by 0, 1, 2, 3. Here, 0th position, first position, okay, 1 shift, 2 shift, and 3 shift. Okay, please see here. Always the most significant bit is here. Okay, by setting the control bits, the S1, S0, S1, S2, S3, these are the control inputs. Okay, 0, 0, 0, 1. Okay, 1, 0, 1, 1. 1, 0 means it's two shift. 0, 1, 1 shift. 0, 0, it's 0 shift. So there is no shift in at the same time, same position. A3, A2, A1, A0, A3, A2, A1, A0. One shift, right side. Okay, this one will come here. A2 will come here. A1 will come here. A0 is discarded. Then in the position of A3, again A3 is placed. Okay, since the circuit for a barrel shifter is a combinational logic circuit, the time taken to implement the shift is the total combination delay involved in decoding the control lines and setting up the path from the input lines to the output lines. This delay is only a fraction of a clock cycle. This delay is a fraction of a clock cycle. Okay. Actually, I have